Hello, everyone. Today we will explore how to use the MCD module to set up a laser marking unit.
In modern manufacturing processes, intelligent laser engraving technology is widely used for precision processing and engraving of various materials. This project system consists of components such as an engraving head, a work table, a drag chain transmission system, and a monitoring display. Materials are transported to the engraving unit via the drag chain, and after precise positioning, the engraving head processes them. The aim of this project is to use PLC to control the MCD model simulation, verifying the operational procedures and work efficiency of the intelligent engraving unit in the production line.
We will cover the following topics. Learning objectives. 1. Master the setup of physics objects, joints, sensors, actuators, and signals in the MCD module. 2. Understand the relationship between signal settings and PLC programming. 3. Learn how to create a new PLC project and configure it in the TIA Portal software. 4. Master how to export signals from the MCD module and create corresponding variables in the PLC. Now, let's look at the specific operational steps. Now we will demonstrate the specific operational steps. Open the laser marking unit model. Click Application, then under Design, select More, and enter the MCD module from the drop-down menu. Next, we will set up the basic physics, including the joints, sensors, actuators, and signals. In the previous case studies, we learned that moving components should be set as rigid bodies, while contacting rigid bodies should be set as collision bodies. In this case, materials on the conveyor will reach the workstation to begin laser marking. Here, we will use object changes to display the marking completion effect. The marking objects are the models, so we need to set up two trays, one for the pre-processing state and one for the post-processing state. Now let's proceed with the setup. Click on Rigid Body. You can select each model individually, but since there are many models, we can go to the Assembly Navigator to select the entire assembly. Copy and paste it. Then select the material after processing. Click Apply. In addition to these two materials, we need to set the two blocking cylinders and the pushing cylinder as rigid bodies. Select all models that can move simultaneously. Then choose blocking cylinder 2. And set it as the same rigid body. For the pushing cylinder, if it's hard to select, you can click the check mark in the navigator or hide it using the icon after setting it as a rigid body. Click OK. Then, show the processed materials. Next, set the areas where the materials, rigid bodies, come into contact with each other as collision bodies. Click Collision Body. Since the materials are moving on the conveyor belt, you need to set the conveyor belt as a collision body. As well as the trays that come into contact with the conveyor belt. Right-click and select from the list. Choose the entire entity and click Apply. Since we've already set it as a rigid body, it will automatically be categorized below. Similarly, set the process tray as a collision body and ensure the blocking cylinder that contacts the tray is also set as a collision body. Don't forget to include the plate of the pushing cylinder that makes contact with the tray as well. Click OK. Since the materials on the conveyor belt are continuously generated, we need to set the unprocessed materials as an object source to ensure continuous flow of materials. Click Apply. Next, we'll set the joints. The blocking cylinder and the pushing cylinder perform an up and down sliding motion. So we need to configure them as sliding joints. Select the connected rigid body as blocking cylinder 1, leaving the base unselected, for we didn't set it as a rigid body. It can be considered fixed, like the ground. So, for the connected body, select blocking cylinder 1 with the vector direction set downward and apply. Similarly, configure blocking cylinder 2 as a sliding joint, also with the downward direction. Next, configure the pushing cylinder as a sliding joint, with the vector direction set upward. After that, we'll set up the sensors. There are 3 trigger sensors, and 1 for object transformation. Let's proceed with each configuration step by step. Select the sensor and specify its orientation by choosing the central point. Since the sensor faces the x-axis direction, adjust its orientation accordingly. We need to change its direction. Click on the circular point representing the x-axis. Then press Enter. Confirm the x-axis direction. Click OK. Here we need to set the center origin again. And the first sensor is set up. Change the name. Click Apply. Use the same method to set up the second and third sensors. The second sensor and third sensor